A quick disclaimer before you watch the video, please stay till the end of the video because there will be a poll in which you can vote which thing I will cover in the next episode of Rocket Monday. Thank you. Now on with the show. Hello YouTube viewers, welcome to my show Rocket Monday. In today's episode we're going to take a look at Space Shuttle, NASA's deadliest mistake. So let's dive right into it. First, you have to understand why they were planning to build Space Shuttle. So they had to retire this Saturn V system, which was an expendable system, basically use and throw sort of system, and it was quite successful, quite safe, however idiotically expensive. As in, if you inflation compensate their cost, you are talking about roughly 1 billion to 1.5 billion per launch. So suffice to say, it was quite expensive. However, it was also a super heavy lift rocket, as in it could send more than 50 tons. How much? Basically, they successfully managed to put 130 ton into low Earth orbit. Suffice to say, this rocket is a big rocket. And here, this image should give you a sense. That's a small truck, size of one of its engine, F1 engine. So they had the system, they got the things worked out, and in the last mission, last launch of this rocket, they sent a Skylab rocket, and basically it was a space station, and they figured it out. They have to build a space station now, and how they're gonna build it, they worked out the logistics. So they had to build a new launch vehicle. So they wanted to retire this, and they wanted to make sure the replacement that they're gonna build would be cheap, as in very low cost. $1.5 billion per launch was not let's just say it was not going well with the senators and the Congress. For that reason, they wanted to make sure the cost is low. Second, how they're gonna make the cost low was they wanted to practice out reusability, how they're gonna recover as much parts of the system as they can. And this was a requirement from Department of Defense. They wanted to create something called quick turnaround time. Basically, once your rocket is used, the next rocket should be sent as quickly as possible. They were aiming for roughly 15-day turnaround. Basically, from first launch to second launch, there should be 15-day gap. Think of it this way: how SpaceX is trying to do 48-hour turnaround, this was the same. And the reason why Department of Defense wanted to create something that quickly, as in that quick turnaround, at that time they were developing something known as Star Wars protocol. They will have high-end ICBM interceptors in low Earth orbit, and because they might have to replenish that if one ICBM attacks happens, because to intercept one ICBM they were planning to use upwards of 20 counter penetrators, because there was no way to get guarantee 100% hit, and one ICBM that goes through you, it's more than enough to do enough damage. So they wanted to make sure that, like, if they have this system, they can quickly replenish it, as in, let's say they spent 50% of the first launch, they're quickly gonna send and quickly build up a shield. So they really at that time really wanted that quick turnaround time. So all these things done, so what design we finalized into is that design. Now, it was using SRB. At that time, many people kind of find it odd. SRBs are not ever looked as a safe alternative for human transport. Like, it's okay if you want to just send payloads, but nobody wants to use that SRB in human rated systems. They have no abort system. Basically, once they light up, they're gonna run as long as they have to, or as long as their fuel is there. So the reason why SRBs were chosen for this system was this was a dual edged sword. Basically, if they were using ICBMs, to test ICBMs, they have to actually launch the ICBM. The problem with that, if you test your ICBM, your opponent, like in that scenario, Russia, will figure out how your ICBM works. That is not a good thing. However, ICBM cannot use liquid fuels, because the liquid fuel available at that time were not very high specific impulse, and not to mention cryogenic, which does have high specific impulse, does not have launch ready alert. So they had to use SRB for ICBMs. Now, how they gonna improve SRB without letting the world know that they are building the ICBM? Implemented in NASA. This was Department of Defense request that use SRB. That's why, like, even though first Saturn system did not use any sort of add-on boosters, they had to use it, because this was like this was a suggestion that was given to NASA. It's like, use SRBs. And second suggestion from Department of Defense, which was the most deadly one, was that they required a specific payload size. not the weight, as in the weight requirement was not that high from Department of Defense. Like, you know, we want let's say 15 tons to low Earth orbit, which is not that high. However, the specification requirement, that the design requirement they said, like the volume, that was way too big, and NASA wanted to remove that simply because if they shrink it down even just few percent, like as in 10 to 30% shrinkage, it will save lot of money in rocket design development, because they were pushing it, like just trying to make that a bit bigger. It was like completely changed the rocket size, rocket volume, rocket usability, everything. So these two suggestions from Department of Defense was kind of a very big design element into the main space shuttle design. And the sad part is, even though the Department of Defense asked them for a specific payload specification, they never used it. And so NASA, after all the specification, they settled onto what's called partially reusable. Basically, they're gonna reuse the most expensive part, which is this engine, the best engine ever built. I mean, like, you can debate around that, but so far this is the best engine, closed cycle engine, and they wanted to recover it. And SRBs, the ICBM technology, basically it will also come to land, and they're gonna recover it. Basically, this is not a reuse system. They're gonna collect it, strip the paint, polish the metal again, rebuild it from ground up. So all they are saving here is just the basically flight data and a lot of metal. But it was, at the end, this turned out so expensive that they are like, yeah, this is why Space Launch System, even though they have same boosters, they are not reusing it. They're like, just use and throw it. Recovering it is so much expensive. So that was the design element. Department of Defense played a very crucial role into it. So what we got in the other end? Well, we got something very slow turnaround. So flat out, once the first shuttle was launched, second and third shuttle, it was quite clear, no matter what happens, they're not going to get the quick turnaround that Department of Defense needed. So Department of Defense flat out is like, no, they started to develop something else. I made a video about that here. And once Department of Defense pulled out, and other things also happened. The first is, it ended up so expensive that it was costing more or less the same, if not more, than Saturn V. And not to mention, this was very dangerous. Like, in less than 200 mission, 2 of them blew up. And this is the first disaster, and this is the second disaster. Now, the sad part about both of these disasters is that it was preventable, both of them. First one, SRB, this was very painful for NASA, simply because there was an engineer that was, as you see many of people working in the flight and control room, there are people who are dedicated to one job. Like, you just take care of the range safety, you take care of the SRB, you take care of the fuel tank, you take care of the engines. So these people are like flight range ready. So engineers, when they saw it, because they had to delay the launch when this shuttle was on launch pad, they had to delay the launch because the weather was not clearing up. So they kept the launch, instead of scrubbing the launch, as in just cancel it, they delayed it. Like, okay, they had the launch window for a while, so they were like, okay, let's wait to see whether the environment cleared up. It does clear up, like, they got the window to go ahead, as in like weather gave them the green light. However, at that time, an engineer called them. It's like, please scrub this launch, because SRB, like this solid rocket booster you see, they are built in segments, and that's where the most SRBs fail. The segment is joined by what's called O-ring. Now, normal SRBs generally use one O-ring. This is a human rated system, so they were building 2 O-rings. However, the engineer specifically called at the time when the shuttle was in launch pad, the temperature, as in the outside ambient temperature, dropped below 0 degrees Celsius, as in ice was falling up, as in the O-rings were compromised. This happened before the rocket was launched. Engineer tried to warn NASA. It's like, bro, just cancel it. Just cancel it. The O-rings are not designed to handle it. Boom, they launched it. This happened. They saw this on screen, and if you see any continuous footage of this, that this starts to leak out, then it seals up, because the soot that is being generated from the SRB sealed it up. But once they reach into high altitude, there is a sort of jet stream, wind hits it, and then it dislodges it. Then it leaks out, and that time SRB is firing at much higher thrust factor, as in like it's much more powerful at that time. It's burning at max capacity. It just punches a hole into the orange fuel tank, and boom. This was 100% avoidable. It's not like somebody could have done differently. Somebody followed the procedure and wanted to stop this launch. This did not happen. Then we come to the second launch. Like after this, NASA took a lot of precautions, lot of measurements were done, and after that, if somebody would have said like, you know, scrub the launch, there was no doubt, it would not, nobody would have cared if you know, a janitor would have said like scrub the launch, they would have scrubbed the launch flat out. They realized people's lives are not cheap, and not to mention that blowing up is also very expensive. So they took a lot of lessons from that disaster. But after that, the idea was like, okay, now space shuttle is, you know, foolproof. But even then, the second disaster happened, and in this scenario, my country lost an astronaut known as Kalpana Chawla, the Challenger disaster. Now, problem in that disaster is that NASA has used what's called range cameras. Basically, there are a lot of cameras that will track the rocket as it goes up, and this is done to track debris, basically what is falling over and all that. So there was debris falling over, and you can find the video footage. I will try to link it below, and you can see there was a debris that hit the wing. This place. This is what's called reinforced carbon. Basically, it's a thermal armor. Now, this thermal armor, it was never tested for what's called bird strike. Basically, bird strike is not same as space strike, but bird strike basically refer to the idea, have you tested it to its breaking point? Basically, in aircraft industry, windshield of the aircraft is generally tested with a bird strike, as in like they will keep the windshield intact and then they'll try to break it using a bird, firing a bird at relative speed, as in if the plane is meant for, let's say, 300 kmph small plane, they will fire the bird at 300 kmph to see whether it can handle that. No such test was done on this, and even though this was on side of a rocket, the reason why you see the orange insulation on the rocket, that's the reason. The insulation was done so there was no icing, like it does not, ice does not build up and then fall, because that will kill the shuttle flat out. So but nobody had thought like, what if the foam breaks off? And it's not like it never happened. Foam did break off, but most of the time it caused no damage. In this system, it did cause damage, and here's the tea. Once the space shuttle reached to the orbit, a lot of engineers go through the footage and be like, okay, let's see what happens, and like, you know, has there something wrong? They also found out there is an issue, something happened. Like there was no absolute detail, there was no like, okay, I am pretty sure wing is compromised. They asked Department of Defense, it's like, can you please, you know, let's look around the shuttle, let's see what's what, and you know, is there a damage or not? The reason this time NASA cancelled that request is simply because they knew even if there is a fault, like something like this has happened, there was no way to save them. So inherently they had this idea of, you know, it's better for them to you know, don't expect anything and just randomly die, rather than you know, be stuck in space until the air runs out. So for that reason, the second disaster happened. So is there a lesson here? Like, why the heck this many things happen? First, the unnecessary Department of Defense requirement. This was the primary factor why a space shuttle was so bloated. They never used it. Second, there were too much optimism into building a, like this is the best example I can show you, is this is what NASA was thinking, like, you know, this is how they're gonna refurbish a space shuttle, this is what they need to refurbish a space shuttle. So this is why, like, there were optimism was way too damn high. Like they were, this is like, even an aircraft needs more maintenance than this, and they're like, we could just gonna open the, you know, cargo bay door and just lower the payload, lock it up, everything good. Too much optimism. And bad management, as I already told you. Like the first one was so obvious that it was like painful. Like somebody is calling you, somebody is telling you, please scrub the launch, and you did not scrub the launch and people died. So, and not to mention, overall, this is what I like about SpaceX, as I made a video about secrets of SpaceX, you can check it out here, is that it's too complex. The reason why SpaceX can successfully even make a cheap rocket, even go to International Space Station and come back and reuse the boosters, is because it's very simple. This system inherently was idiotically expensive. To give you an idea, it has 3 types of engine: SRB, solid rocket booster, then liquid fueled rocket engine, the RS-25. Then it also has orbital class. You see the 3 main engines, then you see 2 small nozzles, those are orbit maneuvering engines. So it had 3 engines. How much engine SpaceX has? 1. Basically, they have 1 type of engine, that's it. They just have 9 in the first stage and 1 in the second stage. So you can see, like, inherently there were so many things into the system, built into it, that refurbishing it was expensive, building it was expensive, everything, every aspect of it was expensive. And not to mention, because this was government funded, let's just say they were not very great with the money. So is there a silver lining of this disaster? Well, yes. First, this forced, as in like this is the sole reason why there is a commercial resupply mission, simply because if NASA successfully would have had built a proper space shuttle that did not have the tendency to kill the astronauts, they would have still used it. Even though it was meant to be retired, they would have successfully delayed its retirement, reused it, and they did not have been put in a situation where they have to go to Russia for their astronaut launch. So this created a scenario, a power vacuum, if you will, where NASA had to create a system to compete from its own ground. Basically, they're like, okay, we can send our own astronauts. So to create that, they created what's called commercial resupply mission, and results of which orbital ATK. And I don't think I need to give you an example of that, but this is Dragon capsule. Basically, this whole thing happened because NASA was forced to privatize. Why they were forced? Because Space Shuttle was retired early without a replacement. Why it was retired early? It was unsafe. And this also forced NASA to do much better management. Now the SLS system is being built from day one for safety, as in like from day one they are making sure that no matter what happens, whatever happens to rocket, whatever happens to the launch pad, they get their astronaut back. The launch abort system has been tested thoroughly, and they are very confident that even if SRB blows up, they can still save the astronaut. And not to mention the engine that we got out of that was phenomenally awesome engine. And as many of you know, yesterday Elon Musk held a press conference where he was talking about Raptor engines and the first private citizen that will go around the moon. The engine, methane powered engine, still does not have the specific impulse of these puppies. These puppies can go up to 452 seconds of specific impulse. Now, of course, that mainly comes from being the fact that they're using hydrogen. Hydrogen gives you the best specific impulse. So as you can see, and this is the core reason why Space Launch System, on which I have made a video here, Space Launch System is using this. This is the best engine that we have ever built. Like, of course, you might say, okay, this engine, F1 engine, may have more power, and this Raptor engine may be cheaper, or things of that nature. But overall, this engine can work from sea level to vacuum, and with this efficiency. So suffice to say, and it's reusable. So suffice to say, flat out, this was the best thing that came out of it. Second best thing for every one of us is that commercial resupply missions, because of which SpaceX is there now, because of which a lot of people are interested in space. So there is a silver lining to this. This was my presentation on the matter, and I would suggest you pay attention to the poll that will appear here, hopefully. And I would suggest, if you liked it, leave a like. If you didn't like it, dislike it, leave a comment. And I would urge you to subscribe, and please press the bell icon if you are free. And as always, thanks for watching.